All right, let me make a video solution for number 31 here. So I guess chapter 28 now, 29 now that we're into magnetism. And number 31, and I better put page 1. I don't think this is a long problem, but it is a pretty tough problem because of the visualization that's going on. Let me just read the problem here. It says it just says here a non-uniform magnetic field exerts a net force on a magnetic dipole. So they just want to show you that there's going to be an interaction between a magnet and a dipole. But here's the problem. It says a strong magnet is placed under a horizontal conducting ring of radius r that carries a current I that is shown in the figure. So I printed up the figures so just I can draw on it and you can see it a little better here. And here is the description that we've got this magnet underneath, and the magnet is going to make this field, and they have the field in green, so I'll draw in green also. They don't draw the whole magnetic field. It would arc around and come like this somehow, and so that would be maybe the whole field. There would even be parts of the field this way. But the main part of this, of course, is the field right where the ring is, because there is an interaction between a current and a field. In fact, that's the point of chapter 29. And so just reading this problem makes me think I better write down this equation. The force is equal to the magnitude of the current times the length vector. That length vector is the length of the wire that's in the magnetic field, where the direction is the direction of the current, and then we cross it with the magnetic field. So that's going to be the force. Because if I go on to read this question, it says, if the magnetic field makes an angle theta with the vertical. Let's go back to our picture. There it is. So the magnetic field is non-uniform, right? These lines are close together here, and then they spread out, so they're angled out. And so right here where the current is, we would have a field, and it's a non-uniform field, and it's at some angle theta, and that's what they're saying. The magnetic field B makes an angle theta with the vertical at the ring's location. And obviously, if this ring was lower down or higher up, this angle would be a little different, which probably is a good thing. We'll just leave it as theta. What is the magnitude and the direction of the resulting magnetic force on the ring? All right, so to kind of help this, and I gonna maybe start with a direction here and draw a picture. But this right here says that the force would be perpendicular to both L and B. And we would have to use our little right hand for cross products, remembering to put our finger in the direction of the first one, which would be the L, and then adjust our wrist until our palm is in the direction of the second one, which would be B. And so B might be something like this. And so then L cross B, and so that you kind of move your fingers to kind of show, okay, this is L. I can close it towards B, so B is in the direction of the palm. And then the force would be in the direction of your thumb. And so, of course, notice that that's perpendicular to the plane that is made by the two. So if I come back in this picture, this might be actually kind of hard to see. But if I were to look maybe at, not the whole ring for a moment, but maybe just this part of the ring right here, a little cross section. And they show the current, which would look like it's coming out. It's why I went to the garage and I grabbed this wire and I thought, well, maybe if I held it here in kind of 3 dimensions, it would kind of show a little better. And maybe this socket extension being the magnet underneath it. But as we look on it, this little point right here is supposed to be where my fingers are holding it together. And this little direction of current is saying the current comes out away from my finger, arcs around, and comes back. And so this little socket extension here, but I'm going to call it the bar magnet. Maybe I'll put it a little bit lower. Looking something like this, then means the magnetic field is angled like that, and the current at this point is coming straight out. So that's the visualization I want you to have. At this point, the current is coming out of the paper, and the magnetic field is arced at an angle. So if I follow the right-hand rule here and put my fingers in the direction of the current, this is coming out, I'd be putting them, this way towards the camera. And then if I hold my wrist the best I can, and then turn my right hand so my palm is in the direction of this green one here. So it looks like that. So my fingers are pointing up, and so here's the ring. Okay, so the current's coming towards you, towards the video camera, so my fingers are up. And I've adjusted my palm so I can then close it, and so there's my thumb. And so my thumb is pointing like that. My thumb then is 90 degrees to the magnetic field. It is also 90 degrees to the current. And maybe if I use this little nail and put it on the paper here, there's the direction of the current. Okay, so this force is 90 degrees to the currents, and this force is also 90 degrees from the magnetic field. And for that matter, I'm hoping you can see also that the currents and the field are also at 90 degrees. I'll need that later when I go to calculate the magnitude of the force. Let me just keep focusing on direction. Because if I did the same type of argument with a little piece of currents over here, and so coming back to this ring, here this current would be this part, and it would be going into the paper. And so if I was using the little screw here, I guess I'd be pointing it down, although I can't let go of this one, it would fall. But with the current going down and the magnetic field, and so here's the magnetic field arcing that way, if I were to take my fingers and put them then into the paper and adjust my palm here so that I can close it towards the magnetic field, and I would get something that would be looking like this. And I'm kind of hoping you would see that all the way around the ring that would be true. And so the first one we did right here where my fingers are holding my loop together, the force would be kind of angled like that. Over here would be angled like that. And at this point it would be angled kind of down into the paper. The current would be going to the left and the magnetic field would be kind of arcing up and out, and so it would look something like that. And you would get this kind of angle. And so you might say all these points are kind of making a cone shape, if you will. And so just looking at the picture, if you take a bunch of forces, you take a force that is going that way, and you add to it a force that's going that way, and you break it down into its components, its vertical components and its horizontal components. The horizontal ones are equal in magnitude, opposite in direction, and they're going to cancel off, but the vertical ones are going to add up. And of course I just drew these two, but if you did the cone all the way around, then the ones arcing in would have a Z components, but they would cancel out with the ones in the back that are kind of arcing out. And so I would say that the force in the x direction cancels off and the force in the z direction cancels off. And really this just boils down to how much force do I have in the y direction. And I think that's the concept of this question, was to show that if you had a magnet, and then of course you have and I'll just say another magnet. This is really what chapter 31 is going to be, that the sources of magnetism come from moving charges. So let me call this a second magnet. They're going to interact. And in this case, I'm concluding that this magnet that is made from this current in the loop is going to be then pushed away. And it's going to be lifted up. When we get into the next chapter, we're going to learn that this current going in a loop is kind of like a permanent magnet, where this end is a north pole and this end is a south pole. So you could kind of say that this is a magnet with the north pole near another north pole's magnet, and of course they repel each other. But that's getting ahead of the game here. All right, so just focusing on this particular chapter, there is definitely then an interaction, a magnetic interaction, that this ring then would be pushed away. And so, again, if this was a magnet, and we had a little loop here, and we put current as shown, it would push this away. Then if the current went the other way, it would attract it. But this one, it's pushing away. And so it's only in the vertical direction. And so I think that answers the part here. Let me just come back to the question. It says, what are the magnitude and the direction of the resulting magnetic force on the ring? So I've answered the part about the direction. It's in the vertical direction. And I wanted to do that one first because I think maybe probably the hardest part of this problem is visualizing that. Now we can go and do the calculation. And it's pretty plug and chug to get the answer here, although the angles are kind of hard to see. And so we're going to be back to the hard part of visualizing what's going on. So let me just do this. Let me just worry now about the magnitude of the force, because then that would be I times, and I'll just write it first like this, the magnitude of the cross product. Now, the magnitude of the cross product is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. And I am purposely hesitating here to write down a symbol for that. Usually when we have an equation and there's just one angle involved, we call it theta. But I don't want to call this theta. And if I looked in the book, the book would call it, the formula would say theta. But they in the problem have given this as an angle theta, but the magnetic field between the vertical. So that may or may not be this theta. And so I don't want to confuse myself. So let me give it a different symbol than theta. And I'll just kind of go through the Greek alphabet. Let me just call it phi then. Because this may or may not, I need to think about it some more. But I do know that this angle is supposed to be the angle between those two. And like I said, if I just looked in the book, they would call it theta. But in my problem, I have a theta. So I want to be really careful. This goes back to my comment about, make sure you understand each of these equations. You're reading these equations. You're not just seeing it as a symbol. In fact, while I'm here, I'll go back to what I had before, which was saying that this screw right here would represent the current coming out, and this would represent the magnetic field. And so what I said earlier was that the current and the magnetic field are at 90 degrees. And so this phi is not this theta. This phi is this angle between this screw, which represents the current, and this green line here, which represents the magnetic field. And it would be a right angle. I can't draw it on the piece of paper. That's why I said I think maybe the hardest part of this, and really all of our magnetism, is thinking in 3 dimensions. Okay, so it's this angle. So this is really 90 degrees. So that makes it easy to calculate. because the sine of 90 degrees is, of course, just 1. So this right here, the current times the length of the wire, which would be this circumference here, and then times B would be then the magnitude of the force. Now, let me also be a little careful here, because as we come back to where we did the direction, what I'm talking about then is the magnitude of this. And as we said, the net force really is not this magnitude, because this can be broken down into an x component and a y component in this picture. And if you take this angle theta, and let me kind of draw it here. There's the vertical. Okay, and here's the magnetic field. Your author is saying this then is theta. And so I guess it means in here would be 90 minus theta, because this is the force and this is the field, and we know from the cross product that the field is 90 degrees from the magnetic field. I guess it would also mean then this angle in here would be theta. And so I'm going to take advantage of that to say then, okay, so the x component is ILB cosine of theta, and the y component is ILB sine of theta. And I should, again, just in passing, point out that notice that I have really two angles that I'm dealing with in this problem. The first sine of an angle happened to come from the cross product. The second place I see a sine, and for that matter also a cosine, is when I'm getting the components of it. Now, I already said earlier that the x component for the force over here on the right would cancel the one on the left, and the one in the front would cancel the one in the back. And so that's why we said that the x component and the z component would be 0, and I'm not even going to worry about those. So then I can get to this, okay? Which maybe, sadly enough, if you were careless, you might have taken the angle between them to be the theta and then got the same thing and then skipped doing the components. And so if you make both those mistakes, if you confuse my phi with a theta and you also make the mistake of not doing the component, you'd actually have the right equation. So in that case, your two mistakes kind of undid each other and you got the right thing. But it doesn't always work out so luckily. So I hope you kind of understand why we have the two angles, and then why the two, the sine is, one from the cross product and one from the component. Now, I suppose the only thing left to do in this problem is to then say, and they don't give any numbers to work with, but the length of it is the circumference of the loop here at 2 pi r. That's what the L is, the length of the wire. And so there we have the force. It's in the y direction. Maybe I'll even say it's up. And so it's the current times 2 pi r times b times the sine of the angle. And again, don't miss those two. This is a 90 degrees. This is the theta. This is the sine because of the cross product. And this is the sine because of the component. All right. Take care.